Hello everyone, I am Tiani Young, and this is my CS441 final project titled Multimodal Rating Prediction for Bangumi. Bangumi is a community-driven site for anime enthusiasts, similar to my anime list, and my project focuses on predicting how the community will rate a show based on its pre-release information. I was motivated by the challenges of the cold start problem in user ratings. For example, look at A Certain Scientific Railgun Season 4 on this slide. It shows an incredibly high score of roughly 9.7, but it only has 6 votes. This score is statistically unreliable and biased by a few early fans. My goal is to build a system that estimates the true audience reception and the rating variance before a significant number of ratings are available. Information available for prediction. This includes unstructured text descriptions, structured metadata like the director and studio, and the cover image. Our target is to predict 2 specific values, the average rating score and the score variance, which tells us how controversial a title might be. This is a multimodal rating prediction problem. As shown here, we take inputs like text descriptions, structured metadata, and optional cover images. We process these through encoders such as bag of words or transformer-based embeddings for text, and then feed them into regression models to output the average score and rating variance. Here is the high-level modeling pipeline. We start with raw Bangumi data, filter it to remove insufficient ratings or not safe for work content, and then move to dataset construction. The text data goes through encoders like TF-IDF or MPNet, while the cover images are processed by CLIP. These features are combined and sent to regression models to generate our predictions. For data collection, I avoided relying solely on the Live API because of rate limits. Instead, I used the Bangumi Archive, a large-scale JSON lines dataset designed for efficient bulk access. Since raw data is not machine learning ready, I performed pre-processing steps, including filtering out non-anime entries and normalizing nested text fields. In the feature engineering stage, I normalized summaries and tags into plain text and handled missing values explicitly. For numeric features like rating counts, I applied log transformation and standardization to handle the data distribution. Categorical features such as the release year and platform were also encoded to ensure the models could interpret them effectively. I utilized different strategies for text and image encoders. For text, I compared sparse lexical representations like TF-IDF against dense transformer-based embeddings like MiniLM and MPNet. For the visual component, I used OpenAI's model to encode cover images, applying dimensionality reduction before fusing them with the text features. For the regression models, I evaluated a variety of families, including linear models, ensemble methods, and neural networks. The prediction setting is a multi-output regression, where the model must predict both score and variance simultaneously. I ensured all models use the same feature representations to maintain a fair comparison. My experimental setup involved splitting the dataset into 70% training, 15% validation, and 15% testing sets using a fixed random seed. To measure performance, I used mean absolute error and root mean squared error as my primary evaluation metrics for both the score and variance targets. This table shows the best part of overall results on the test set. You can see that the light GBM model using MPNet embeddings achieved some of the best results. Interestingly, adding clip image features did not always improve performance and sometimes resulted in higher error rates compared to using text features alone, suggesting that the metadata and text summaries are the strongest predictors. In contrast, the MLP model performed relatively poorly, likely because the feature space is high-dimensional and complex, while the dataset size is limited, making it difficult for neural networks to generalize effectively. Finally, the full code repository and data sources are available via the links on this slide. I utilize libraries such as Sentence Transformers, Scikit-learn, and Light GBM to build this project. Thank you for your time.